Hi everyone, I'm Jasmine and I'm an R&D engineer at Sorrento and Comtek Networks and a PhD student at Bangor University's DSP Centre. So the DSP Centre is a pioneering multi-million-pound research centre within Bangor University School of Computer Science and Engineering, driving world-leading innovation in advanced communication networks. Sorrento is the UK's only manufacturer of WDM, ROADM and GPON solutions and has a long-standing reputation for high-performance fibre technology. Traditionally focused on robust fibre infrastructure, Sorrento is now entering an exciting new phase, integrating sensing capabilities directly into their products. So data is signal-based distributed fibre optic sensing. Through our partnership with the DSP Centre, we're transforming fibre networks from passive cables into intelligent, self-aware systems. Essentially, we are enabling the data-carrying signal itself to act as a sensor, detecting faults, vibrations, and security threats without interrupting a single byte of live traffic. So today, I'll briefly walk you through how this innovation directly impacts the future of our fibre networks. Specifically, I will cover the challenge, why traditional fibre maintenance is costly and disruptive, the innovation, how we use data-driven sensing to monitor networks in real time without extra downtime or fibre resources or extra wavelengths, and the application, how this technology scales from simple fibre maintenance to smart city monitoring, tracking roadworks, health of our utilities that run alongside the fibre. So across the UK, thousands of kilometres of fibre optics run beneath our feet, under the very roads and bridges we use to get here today. The infrastructure supports everything from emergency services and smart motorways to industrial hubs. But these assets are vulnerable. They are roadworks, ground movements, or even improper handling can cause macro bends and fibre misalignments, fibre breaks, and dirty connections. The stakes are high. Service disruptions are not just an inconvenience, they are economically damaging. With a third of all outages caused by physical fibre cable problems, reducing the mean time to repair isn't just a technical goal, it's a business necessity. So distributed fibre optic sensing. Every fibre contains microscopic imperfections, tiny echo points in the fiberglass. Distributed fibre optic sensors turn these flaws into a strength. Instead of ignoring them, we use them to sense what's happening along the fibre. So imagine shouting into a tunnel and listening to the echo to figure out where the walls or obstacles are. Distributed fibre optic sensors does this with light. A high-powered optical pulse travels down the fibre. These imperfections send faint echoes, known as relay backscatter back. By measuring how long it takes for each echo to return and how strong it is, we can pinpoint exactly where the bend, break, or vibration is occurring. The fibre effectively becomes its own sensor, helping us monitor its health and surroundings. However, the high cost of deploying conventional distributed fibre optic sensing in dedicated sensing fibres and the degraded transmission performance when using separate wavelengths remains a major obstacle, limiting its widespread application. Our breakthrough is data-driven sensing. We don't need extra fibres, extra lasers, or downtime. We use the live data carrying signal itself as the sensing tool. The three-stage solution. So our integrated solution operates in three distinct phases to ensure total network visibility, beyond simple maintenance into a critical security tool. The first one is fault and threat classification. With a 98% accuracy in lab tests, we can automatically distinguish between soft failures like a bend and mishandling, and hard failures like a break, and external vibrations which could be caused by roadworks that are occurring alongside the fibre. Fault and breach localization. But knowing the fault exists isn't enough. Operators need to know exactly where it is. We achieve a 98.6% accuracy in locating events, mapping power fluctuations to distances along the fibre. This gives actionable intelligence, directing maintenance crew to the precise repair location or pinpointing the exact section of the link where the physical breach may be occurring. Reflection localization. For harder to diagnose issues such as breaks, eavesdropping attempts, or dirty connectors that generate strong reflections, we can use a correlation-based processing. By comparing the reflected signal to the original data signal, we apply the optical equivalent of a sonar, enabling precision fault localization and isolation and reducing the troubleshooting time, even over spans exceeding 100 kilometers. So the future, smart cities and beyond. While we are optimizing the fiber maintenance solution, the next phase of our roadmap focuses on transforming these networks into a regional nervous system. We're now extending our research into advanced vibration sensing, exploring how analyzing the byproducts of the data carrying signal itself can detect, localize, and classify activity around the fiber. That includes roadworks, events near the fiber, as well as utilities that run alongside the fiber. Ultimately, we're moving away from reactive repairs and towards condition-based monitoring. By using the existing fibers to monitor these structures 24/7, we're essentially giving them a digital voice. Instead of waiting for the manual inspection to find a fault that has already developed, utilities like gas and water pipes can tell us exactly where the leak is while it's forming. And we get this from shifts in our vibrational data. This allows us to intervene early and perform minor maintenance rather than waiting for a major failure, ensuring the safety of our networks, extending the lifespan by decades, and avoiding massive costs of emergency large-scale fixes. We can see on the screen that there's a section which is bridge monitoring, and this is results that we've gotten over the Menai Bridge and the Britannia Bridge in Anglesey, because that's where Bangor is based. And we've also got below that traffic monitoring. And we can see the lines are basically cars going over the bridge or across the road, and we can see the direction that they're traveling as well. And we can decipher if it's a heavy vehicle like a bus or a truck, or if it's a motorbike or a car, or if it's just someone walking. And we can also identify potholes as well. So what started as a simple cable for carrying data is now becoming a powerful sensing platform. Through a partnership with Sorrento, Comtek Networks, and the DSP sensor, we have shown that fiber can do more than just transfer information. We can protect the infrastructure that keeps the UK moving. By turning existing fiber into a real-time monitoring system, we're reducing the downtime, cutting the maintenance costs, and enabling predictive intelligence for roads, railways, and bridges. This isn't just about fixing faults faster. It's about building a smarter, safer, and more sustainable network for the future. The vision is clear. From fiber maintenance to smart cities, we're transforming passive infrastructure into an active nervous system for the region. So we would love to collaborate and explore the new applications for this research. So if you can think of any ideas or have any new applications, please feel free to get in touch. My email's there, the websites of the company and the DSP Center is there as well. I think also Bangor University's website is also there. Thank you for listening. If you've got any questions, please ask.
Hiya, Rob Evans from JISC. This is really, really interesting. So I'm kind of wondering a couple of things. First of all, how does this, presumably something that fits in a transceiver or something close to it, compare to distributed acoustic sensing, which requires half a rack of high-powered stuff and a lot of storage? And given you're still talking about shooting a high-powered pulse down the fiber, does it cause any kind of non-linear effects that affect other wavelengths on the fiber, coherent wavelengths?
Sorry, could you repeat the question? I'm finding it difficult to hear.
Okay, yes. Sorry, I'm getting a bit of my own echo back as well. How does it compare to distributed acoustic sensing, DAS, given that you're doing something in a fairly small unit here compared to large racks worth of kit?
So this one, distributed acoustic sensing, is when you send a high-powered pulse through the fiber, which can interfere with other wavelengths. So we're looking at byproducts of the data carrying signal itself, instead of a high-powered pulse. So we're not needing any extra wavelengths or anything, and we're monitoring the byproducts to get more of the information. In terms of, because I think the exact, what we're comparing this one to would be OTDR. When you've got a fault, you'd plug in OTDR, and then you'd find the fault, and it was also sending a high-powered pulse, but it'll only tell you kind of the breakpoints of it. So we're trying to find a continuous monitoring solution that can complement that, instead of having to have the downtime when you don't need it.
Okay, thanks.
Thank you.
Hello, Greg Choules, ISC. There is a definite echo going on here. Thank you, great talk, amazing applications. You gave some figures about accuracy earlier. I just wondered what your range of error is.
So for the reflection localization and the bend and hard failure localization, we've got it 1.4% resolution, but we are optimizing it and improving it at the moment.
Okay, and just a mad thought about a potential application, tall buildings and their performance over time.
As in a structural?
Yes.
To check its structure. We haven't actually thought of that application. So that's definitely sounds really interesting to investigate. Thank you.
Thank you.
Any further questions? Anything from Slack? No?
If anything comes up, please feel free to email me. Okay. Thank you.
Okay.